Hello YouTube, this is just a quick introductory video to the concept of dynamic optimization. In this video I'm going to be talking about calculus of variations. Okay, so here's the thing. 1 year from now I'm going to buy my first car. And a lot of the money will come from selling beer. See, right now in my room I've got 1,000 cans of Heineken beer. And I intend to sell that to my underage friends. They're willing to pay a ridiculous sum of money for a can of beer, up to $10. If I charge $9, I'll probably be able to sell 1 can a day. If I charge $8, I'll be able to sell 2 cans a day, and so on and so forth going down. So in other words, if Q of T is the number of cans of beer that I've got stored up in my room on day number T, then you could say that negative dQ dt is the number of cans of beer that I am able to sell on day number T. And I'm telling you that will be 10 minus the price on that day that I want to charge. Okay? So I could rearrange this formula and say the price that I will be able to get is 10 plus, and I'm just going to write x or q dot to mean dq dt. Okay, so I get this money. What am I going to do with it? I'm going to put it into my bank account and earn 5% interest on it. Okay, so I want to buy my first car 365 days from now. I've got 1,000 cans of beer to work with, and I've got a bunch of underage friends to work with. This is the price that they're willing to pay if I want to sell this much beer. And I get 5% interest on the money that I collect early on. So what should I do? How should I space out my sales? How should I choose my pricing strategy over time to maximize my profit? Okay. To answer this question, what we have to do is calculate what my profit actually is going to be. Okay, so I already said that negative Q dot is the number of cans of beer that I'm going to be selling on day number T. And I said just a minute ago that the price that I'll be able to collect if I want to sell this much is 10 plus Q dot. So this is the amount of money going into my bank account on day number T. And of course, I earn 5% interest. Let's take this to be a present value calculation. So I have to sum all these little increments of money that I get over 365 days. This is the quantity that I want to maximize by choosing this function, Q of T. I'm going to be coming back to this problem towards the end of this video, but first let's talk about the general problem. So we have some defined time period from 0 to capital T. And we have this thing inside. Let's call it curly L. It's got a special name. It's called the Lagrangian. And this function inside can depend on a number of different things. The Lagrangian at any time can depend on our choice of Q of T. It can depend on Q dot of T. And it can even depend directly on time. And the thing that we want to maximize is this integral from 0 to capital T, our defined time frame. We want to maximize the integral of the Lagrangian by choosing the optimal function, Q of T. This quantity, S, is called the action. So we either want to maximize the action, or in some types of problems we might want to minimize the action. Okay, so in some sense, S is a functional. A functional is a mathematical object that takes a function and it spits out a number, whereas a function is a mathematical object that takes a number and it spits out a number. Now, you might remember a similar problem to the one at hand that you learnt about in high school, where you were given a function and you were asked to find the optimal number to put into that function to either maximize or minimize the function. And you might remember that the condition that a maximum or a minimum should satisfy is that if x star is the minimum, if x star is the optimal choice for this value, then the derivative of the function with respect to x, evaluated at x star, must be 0. We're going to apply a very similar principle to the problem at hand. Suppose I told you that q star, I gave you a function and told you that q star, a function of t, is the optimal choice for q of t. It must therefore be the case that the action you get from q star is greater than or equal to the action you can get from any other function. Or if we were trying to minimize s, then this inequality would be reversed. But let's just go with maximizing for the time being. So we could compare this against this other function, where we've picked a real number, k. Let's take k to be positive, and we've picked some other function, any function at all, epsilon of t, the variation. So we're going to take q star, the optimal, or so I claim, and we're going to modify it slightly. And it must be the case, unless I'm lying, that the action you get from this modified suboptimal function is going to be worse, as must this other modified function, which is also suboptimal. So unless I'm lying, this inequality must be true and this inequality must be true. Well, let's suppose I bring this over to the other side. And I bring this over to the other side. And then I divide both sides by k. So if we take so we're manipulating these inequalities, and both of these inequalities must still be true unless I'm lying. Okay? So what we can also do is we can take the limit as k tends towards 0 from the positive side. So at all times, k is a positive number, so both of these inequalities must still hold. Well, if you think about q star as a fixed function and epsilon as a fixed function that we've chosen, then s of this function really is just s as a function of k. K is the only thing that can vary here. And the key thing to observe is that this quantity and this quantity are the same thing. They are the derivative of s with respect to k, evaluated at k equals 0. So this quantity is this derivative, as is this quantity, evaluated at k equals 0. So if this has to be less than or equal to 0, and that same thing has to be greater than or equal to 0, then there really is only one value that this derivative can possibly be allowed to be, and that is 0. Now, with the problem of minimizing, we could apply the same logic, except with the inequalities reversed. And in that particular case, we get the same result. Okay, let's reiterate. S is the action. It is defined as the integral from 0 to capital T of the Lagrangian, this curly L, this function of q, q dot, and t. Our goal is to find the function q of t that will maximize or minimize s. And we can construct q of t to be a linear combination of q star and epsilon for any real number k. If q star is fixed and epsilon is fixed, then s is really just a function of k. If I'm going to assert that q star is the optimal choice for q, then s of k has to achieve its global maximum at k equals 0. If it didn't, if it achieved its global maximum or global minimum somewhere else, then q star plus k epsilon t would be a much better choice for q than just q star by itself. So that can't be true. Now, if s of k is to achieve its global maximum at k equals 0, then it is necessary but not sufficient that ds dk at k equals 0 equals 0. How do we take this derivative? Well, we apply the multivariable chain rule. dl dk depends on two different pieces, dl dq dq dk, and dl dq dot dq. These latter two derivatives are just epsilon and epsilon dot respectively. So here we have it. This derivative has to equal 0 for any choice of epsilon of t. It becomes more obvious what q star needs to satisfy when you apply integration by parts. You get a term which is not underneath the integration symbol, which is just the antiderivative of this multiplied by that, and you get a term that is underneath the integration symbol. The derivative of this times the antiderivative of that, and you keep the integration. So here you see the term here. And we can factor out the epsilon of t. So here is the thing to observe. If epsilon of t is allowed to be anything at all from 0, for t from 0 to capital T, and it's allowed to be anything at all at its start point and anything at all at its end point, then the only way that this thing here, which is the same as this, the only way that this could possibly equal a constant number, 0, is if this quantity here is equal to 0, and this quantity here is equal to 0, and this quantity here is equal to 0. If any of them were not equal to 0, then we could choose epsilon to violate the rule that this quantity has to equal 0. So, these are the conditions that Q must satisfy. This is called the Euler-Lagrange equation. This is called the start point and the end point condition.